Hello all. Today I'm making an exception in that a viewer has requested past Unit 2 papers, okay? And the truth is that I don't have a lot of Unit 2 past papers for some reason. I mean, from Edexcel, okay, the international Edexcel curriculum. And I wasn't planning on uploading a Unit 2 paper. I was actually planning on a Unit 4 paper and also some other research topics. So recently I uploaded the research paper and people liked it. So I was planning on uploading something related to that. And also it's 30th of July, and here in Cyprus, the outside temperature is the same as the center of the sun. So it's really difficult to keep working. So, but anyway, I'm gonna make an exception and upload this Unit 2 paper for my viewer, who I think that he or she, I don't know, watches. What else? I don't want to create a habit in that though. I mean, because people sometimes, they request things all the times. I'm not making anything from this channel yet, so I cannot really keep up. I have other things to do, or I try to have other things to do, etc. But anyway, let's dive in. The usual thing I always say is that the exam lasts for an hour and 30 minutes. That's 90 minutes, okay? 90 minutes for 80 marks. Okay, so it's almost a no-brainer that you should spend about a minute per mark, okay, to stay on time and in order to finish all the problems, okay? So if a question awards 10 marks, it should take you about 10 minutes. If it takes you 12, it's not the end of the world. 15 is not the end of the world either, but 20 is the end of the world, because then you will run out of time, okay? So try to pace yourselves. Start the paper by working on the problems you know how to solve, okay? Problems that look familiar, problems that you're comfortable with. Skip those that you can't, okay? Don't waste time if you get stuck, okay? Because time is marks in this case, it's not money. Time is marks, okay? So work on the problems you know first, build momentum, confidence, and come back and solve the problems that you don't know how to solve at the end of the paper. Read all questions thoroughly, okay? Half the answer is in the question, okay? Don't forget that. Be certain that you understand what they are asking you to do. And finally, the other thing I always say is that sometimes just by going to the back of the paper, where I am going right now, okay, you will see a list of data over here, right? You have many formulas from Unit 1 and then Unit 2, etc. So try, I mean, even if you don't understand anything about the problem, try to skim through the formulas, find the one that looks more suitable and test, like try to see, does this fit my problem? Can this solve my problem, etc. And that usually helps to answer questions. Okay, I think I'm done. Am I done? Let's see. By the way, let's jump into section A and question 1. But before I say that, the other thing I have in mind is that in section B, I mean, this does not really apply to section A, because section A involves short problems. So sometimes the part B of a question, so for example, in one of the long questions, okay, the part B might actually guide you in finding what the answer to part A is, okay? So that's the other thing to keep in mind. And now I'm done, okay, and ready to start solving problems. I'm sorry for this long introduction. So question 1, the refractive index of vegetable oil is 1.47. Which of the following is the speed of light in meters per second in vegetable oil? Okay, to find this, we will use the definition of what index of refraction is, which is the speed of light in vacuum over the speed of light in the material in question. Okay, so the speed of light in the material in question is c over n, or 3 times 10 to the 8 meters per second over 1.47, which yields 2.04 times 10 to the 8 meters per second, which is option B. Okay. 2. A ray of light is incident on the boundary between Perspex and air, as shown. What is Perspex? I think it's some sort of plastic, but let me know in the question, in the comments. The angle of incidence I is greater than the critical angle for the Perspex air boundary. Okay, so that's the key there. The angle of incidence is greater than the critical angle. Okay, so what does that mean? Let's read the answers. Which of the following statements is correct? A, all the light is refracted. No. B, all the light is transmitted. Also wrong. And C, all the light is reflected. That's it. That's the correct answer, because the incident angle is larger than the critical angle, okay, for total internal reflection. And then D says some light is reflected and some light is refracted. That's wrong. Okay. Another thing about the multiple choice section, it's often the case that you can eliminate all the wrong answers and arrive at the correct answer, okay? I mean, this is not true here in this problem, because you need to know what the critical angle is, but there are cases in which that mentality helps. Okay, 3. Which of the following units is equivalent to the coulomb? Okay, to the coulomb. So amperes over seconds, that would be coulombs over seconds, and then again over seconds. So A is wrong. Okay. Then B, joules per volt. Okay, so joules per volt. We have to recall what the definition of a volt is. So 1 volt means that the battery provides 1 joule of energy to 1 coulomb that passes through it, or that is pushed through it. So joules per coulomb, so that works actually. So B is the correct answer. Okay, moving on. 4. A student sets up an apparatus shown, the apparatus shown, excuse me. When the string is plucked, it vibrates with a frequency F. Which of the following single changes would increase F? Okay, there are many options there, but it doesn't make sense to read them until you write down the math. So the speed of the wave, sorry, in the string is equal, sorry, with the wavelength times the frequency. Okay, and this speed is actually, let's write it like this. And this speed is equal to the square root of the tension over the mass per unit length mu. Okay, but the tension is provided by the mass, the weight of the mass, so mg over mu. So if we combine these, we find that F is 1 over lambda times the square root of m times g over mu. Okay, and also I'm gonna need a clean page. I'm sorry about that. So that's 4. And also recall that lambda is equal to 2 times L for the fundamental node, okay, in the string. Okay, so F is therefore 1 over 2L times the square root of m times g over mu. Okay, so let's go read the answers now. Okay, A, decreasing the length L. Okay, so if L decreases, F increases. Okay, which is exactly what they ask, right? So A is the correct answer. Now let's read the other ones, because I want you to see something. Decreasing the mass M will actually decrease the frequency, right? Because F is proportional to the square root of M. So B is wrong. C, increasing the cross-sectional area of the string. Okay, now one might be inclined, okay, it's still the wrong answer. I mean, C is a wrong answer, but I want you to see something related to C. How does the cross-sectional area of the string come into this picture? Okay, so let's see. Mu is mass per unit length, right? And then the density of the material with which the string is made is equal to the mass over its volume, right? So we actually see that mu, the mass per unit length, can also be expressed as the density times the cross-sectional area. Okay, so if we put it up here, okay, if we put this information up there, we see that F is 1 over 2L times the square root of m times g over rho times the cross-sectional area, okay? And they say that increasing, if A increases, actually F decreases, right? Okay, so that's good to have in mind. I've never seen it in other past papers, so it's important, I guess, because maybe it will come up in a future paper. So I wanted you to see that the mass per unit length can also be expressed in terms of the cross-sectional area, okay? So C is still wrong though. I hope I didn't confuse you. And then D says increasing the mass per unit length of the string. Again, this will decrease the frequency, so that's wrong. Now let's move on to the next question, which is 5, okay? Okay, 5, an energy level diagram for the hydrogen atom is shown. Arrows A, B, C, and D show 4 possible electron transitions. Which transition would result in the emission of a photon with the shortest wavelength? Okay, first of all, before we do anything here, 2 out of these 4 transitions make absolutely no sense, okay, and should not be there. Which ones are they? Pause the video, write the answer, write the wrong answer in the comments, and then come back and I will tell you, okay? So B and C are wrong, okay? Because these are not transitions in which photons are emitted. Actually, photons are absorbed. Actually, the electron absorbs energy either via a collision with another electron or by absorbing another photon, etc. So that's not a transition where light is emitted, okay? So A and D are the only possible answers. How will we know which one is the correct? So delta E, okay, the change in energy, is h times the frequency, which is h times c over lambda. So lambda, okay, is h times c over the change in energy. So if delta E increases, lambda decreases. So the shortest wavelength is emitted by this transition. Okay, so that's A. For those of you who are going to go study physics or chemistry, maybe some fields in engineering, maybe material science or material engineering, if something like that exists. Anyway, people who will learn quantum mechanics, it's one of the most basic things you should know. The energy of the ground state of the hydrogen is minus 13.6 electron volts. Okay, so this is a very well-known number. If you are really nerdy, you will remember the first excited at minus 3.39 electron volts, and the other ones too. I mean, if you are really nerdy, okay. And yeah, I mean, I'm not gonna say more. Let's stop here and move on. Okay, 6. A negative temperature coefficient thermistor is connected in a circuit as shown. Okay, the temperature of the thermistor is increased. Which row of the table gives the changes to the readings on the ammeter and the voltmeter? Okay, so negative temperature coefficient thermistor means that if I plot the resistance with respect to temperature, we will see a decreasing curve like that, okay? Which means that the resistance decreases. Why? The reason is that these thermistors are made of semiconducting materials that have the property that if you heat them up, electrons go into the conduction band of these materials. So there are more electrons that can carry current, okay? So the resistance reduces, okay? Okay, now we have here, we have 2 resistors, right? So in series, so R total is equal to the R plus the R of the thermistor. So if the resistance of the thermistor decreases, so if R thermistor decreases, then the total resistance also decreases, right? Because the other resistance is fixed. And I, which is equal to the voltage over the total resistance, increases, okay? Why is that? Because we decrease the total resistance, right? Okay. Now the potential difference across the thermistor is equal to the current times the resistance of the thermistor. Okay, so if we plug in, we get we have to plug in this, these two. We take these two, sorry, and plug them in there. Okay, so we will have V over R plus R thermistor times R thermistor. Okay, and now I'm gonna need a clean page. Okay, so V across the thermistor is R thermistor times V over R plus R thermistor. So if we make R thermistor the common factor in the denominator, we will have R thermistor times 1 plus R over R thermistor. I hope I didn't lose you yet. Okay, so this cancels, and we see immediately that if R thermistor decreases, okay, then R over R thermistor increases. Okay, so the voltage across the thermistor decreases. Okay, so I hope this makes sense. As now we have to read the table there. So we need the current to increase. So options C and D are the only ones that work. And we need the voltage across the thermistor, which is what's measured by the voltmeter, to decrease. So option D is the correct one. Okay, so this took a little bit longer. I mean, okay, remember my rule. This should have taken 1 minute. It took us maybe 3. It's fine. Okay, things like that will happen in a test. Okay, let's move on to the next question. 7. Two waves of wavelength, 2 meters, are produced by a source at point X as shown. Both waves are initially in phase. The waves travel different distances at at point Y. Which of the following is the phase difference in radians between the two waves at point Y? I'm going to show you 2 ways to solve this. So the change in phase is equal to 2 pi over lambda times the distance difference. Okay, so 2 pi over 2 y2, because 2 is the wavelength, okay, times the distance difference, which is if the wave takes this path, it covers 9 meters. If it takes the other path, 4 plus 4 is 8. So 8 and 9. Okay, so 9 minus 8 gives us immediately pi. Okay, so the correct answer is D. Another way to do this, which might be easier, is to realize that lambda is 2 meters, right? And you can draw it actually. Okay, so that's 1 lambda. Okay, so that's 1 lambda. You see that 1 lambda corresponds to 2 pi if it was a sine function, right? And in this case, you have delta x equal to 1 meter, which is lambda over 2, right? So lambda over 2 means that's lambda over 2, okay, this distance over here. What's that in radians? It's pi, okay? If this was the sine function, the phase would be pi. I hope this makes sense. So also D, okay? So 2 ways to find this. I prefer this one actually, okay? So, but you can use either. I mean, both of them are correct, okay? 8. The cell in a solar-powered lamp stores 6 kilojoules of energy. The lamp is switched on and the cell discharges fully. The cell has a constant electromotive force of 1.5 volts. Which of the following is the charge that passes through the lamp? We commented earlier how the volt is actually a measure of how much energy is given to some coulombs that pass through it. Okay, so we're going to use that. So we have that the energy is 6 kilojoules and the EMF is 1.5 volts. Now the energy is actually equal to Q times the electromotive force. So Q is given by 6,000 joules over 1.5. So joules, and then the volt is joules per coulomb, right? So this is 4,000 coulombs. Okay, so that's the, and you can use dimensional analysis here as well, because you are given two numbers, 6,000 joules and 1.5 volts, which you can write as 1.5 joules per coulomb. I mean, this is how physicists think, okay, most of the times. Okay, they are asking for a unit of charge, right? So how do we arrive at such a unit using these two numbers? If we multiply them, we'll find something. So if you multiply 6,000 with 1.5, you will find joule squared over coulomb. That's not useful. What else can we do with these two numbers? We can add them. It doesn't make any sense to add them because they have different units. So it's like comparing apples to oranges, as they say. Okay. And the other operation you can do with these two numbers is to divide them. Okay. So if you divide them, 6,000 joules over 1.5 joules per coulomb, you find a quantity that has units of coulombs. Okay, so that's the correct answer. Okay, so even without knowing anything, okay, thinking as a physicist, you should be able to find this. Okay, moving on to question number 9. When monochromatic light is incident on the surface of a metal, photoelectrons are emitted. Which of the following statements is correct? Okay, A, the maximum kinetic energy of the photoelectrons depends on the intensity of the incident light. That's wrong, okay? And actually, this was one of the reasons why the photoelectric effect was discovered, because they tried to explain it that way and it didn't make any sense. What does depend on the intensity of incident light is the number of photoelectrons emitted, provided that the photons have the necessary energy to extract those electrons from the metal. So A is wrong. B, the number of photoelectrons emitted per second depends on the frequency of the incident light. Again, that doesn't make any sense. So B is wrong. Okay. C, the maximum kinetic energy of the photoelectrons depends on the frequency of the incident light. That's totally correct. And the reason is that, remember that the energy of the photon is given to the work function, the energy needed to extract one electron from the metal, plus the kinetic energy max of the photoelectrons. Okay, so it totally depends on the frequency of the incident light. D, the number of photoelectrons emitted per second depends on the work function of the metal. No, that's wrong. Okay, 10. Two wires, X and Y, are made of the same material. The wires are connected in series. The current in the wires is I, as shown. Wire X has twice the diameter of wire Y. Okay. The mean drift velocity of electrons in wire X is V. Which of the following is the mean drift velocity of electrons in wire Y? Okay, first of all, the current in section X and section Y is the same. Okay, so if we are dealing with section X, we have that the current is equal to the number of conduction carriers per cubic meter times the charge of those carriers, which is E, times the drift velocity, times the cross-sectional area of X, which is going to be pi r squared, right? R squared. Okay, now Y, in section Y, the current is going to be equal to N, again, because it's the same material, times E times Vy, okay, times pi times r squared over 4. Why? Because it's half the diameter. So if it's half the diameter, it's half the radius as well, right? Now let's divide these two. So I cancels, so we have 1 is equal to N cancels, E cancels, pi and r squared cancel, and we are left with V over Vy over 4, okay? But we are interested in, what are we interested in? So we have 4 goes to the numerator, so 1 is 4V over Vy. So Vy is 4V, which is D. Okay, hope this makes sense. Let's move on to question 11, which is section B now. Okay, question 11. A wire has a resistance of 65 milliohms. The length of the wire is 0.25 meters. The wire has a circular cross-sectional area. Calculate the diameter of the wire, and they give you that the resistivity of the metal of the wire is 5.6 times 10 to the minus 8 ohms times meters. Okay, the resistance is equal to the resistivity times the length over A. So A is resistivity times length over R. Okay, and the area is pi d squared over 4, and this is equal to 2 rho times L over R. So D is 4 times the resistivity times the length over pi times the resistance, and we have to take the square root. I hope I didn't lose you yet. Okay, so that's the square root of 4 times 5.6 times 10 times 10 to the minus 8, excuse me, ohms times meters times the length, which is 0.25. So we have meter squared, and these units are under the square root, okay? And then over 3.14 times 65 times 10 to the negative 3 ohms. So ohms cancel, okay? And we arrive at D equal to 5.24 times 10 to the negative 3 meters, which is the answer. Okay, moving on, question 12. A student uses a ray box to direct an arrow ray of light onto the surface of a glass block, as shown. Okay, determine the angle of incidence. I will have to do something I hate, which is to use the protractor. So, okay, first of all, let's draw this vertical line, because that's the angle of incidence, right? Okay, and you will need a protractor. Okay, so let's oh god, this is really hard. Okay, so this is what I'm trying to do. Okay, 143. So we have to subtract 180 minus 143. I hope you have something better to use. So 37 is actually okay. Let's take this away. So 37 is this angle. Okay. So the angle we are looking to find is this one. So 53 degrees. Okay. So I hope I didn't confuse you. It's much easier to use a protractor on the screen or on the paper, whatever it is that you're using. Okay, calculate the angle of refraction in the glass block. Okay, Snell's law says that the index of refraction of air times sine of 53 degrees is equal to, okay, actually I'm gonna write 1, because that's the index of refraction of air. It's going to be 1.5, the index of refraction of glass, times sine of theta r being this angle. Okay, so sine of theta r is sine of 53 degrees over 1.5. So sine of theta r is, let me use my calculator really quick. So theta r is 32.17. So 32.17 degrees. Okay, and because you have to use a protractor, they allow for some minor changes. So if you find 33, I bet it's fine. Okay, moving on. Part B, the light from the array box is unpolarized. When reflected by glass, some of this light will become polarized. Explain the difference between unpolarized light and polarized light. So light, okay, is made of oscillating electromagnetic fields vibrating as the wave moves forward. Okay. Okay, I'm gonna use a clean page, it's easier. So in unpolarized light, okay, these oscillations happen at multiple planes as the wave moves. Okay, I'm gonna try to draw it for you. So what this means is that, okay, this is the direction of propagation, say, okay, and this is one plane, okay. So you will have light oscillating inside that plane. But then maybe you have another plane at some angle to this plane that we just drew, okay? And light will be oscillating in that plane as well. And you can imagine an infinite number of planes. So maybe, I don't know, can I draw another one? I can't, but you can imagine it that you will have multiple planes and the light oscillates in those planes, okay? Usually they have this, the standard way to show this is to have a line and show the wave like this, okay? So that's unpolarized light, meaning that it oscillates in all different planes, pretty much, okay? Now in polarized light, okay, the oscillations are only happening in one plane, which includes the direction of propagation. So again, if we draw it, this is a line, okay, usually they show polarized light like this, which is a correct picture actually, because we can draw a plane, a plane, okay, which includes these oscillations, right? So oscillations are only happening in this plane, okay? So if I come to this plane that we showed earlier, the red one, that is at some angle with, makes some angle with the initial plane, there will be no light oscillating in that plane whatsoever. Okay, so that's the answer. Okay, I think there is another part to this question. Let me see. Yes, there is a part 2. Okay, part 2. The student uses a polarizing filter to view the light reflected by the glass block. Explain what she would observe as she rotates the filter. So first of all, let's write that as she rotates the filter, okay, brightness rises and falls. Okay, so that's the first thing. So brightness goes from maximum to minimum and back to maximum, okay, every 90 degrees. Okay, so to show it, so this is the polarizing filter. It allows light that oscillates in that direction to pass through, okay? So when the light, okay, let's assume that the light oscillates in this direction that I'm showing with purple. Okay, so in this arrangement, we will have a maximum. Now, if we rotate the filter by 90 degrees, then the filter will look like this, okay? And no light will go through because light oscillates in a different direction. So there will be a minimum there. Notice that we rotate by 90 degrees. And then if we rotate again by 90 degrees, okay, the filter now points in the original direction, right? Okay, so 90 degrees. So this direction allows all the light to go through. So we're gonna see a maximum, okay? The student. All right, so this was question 12. Let's move on to question 13. Okay, concrete is often used in building construction. I mean, the way they stated it is like it's a novelty or something. Concrete is almost in every building on the planet, probably. I don't know. I think so. Anyway, after several years, concrete may develop cracks. Ultrasound can be used to find these cracks. And transducer, sends pulses of ultrasound into a piece of concrete as shown. Okay, The transducer detects pulses of ultrasound reflected from the crack. To be detected, the reflected pulse must not overlap with the pulse emitted by the transducer. Okay. In this piece of concrete, the speed v of ultrasound varies with temperature as shown. Okay. So the speed increases with temperature. Interesting. So a pulse of ultrasound is incident on a crack in this piece of concrete. The crack is a distance of 4 centimeters from the transducer. The temperature of the concrete is 23 degrees. Deduce whether the transducer can detect ultrasound reflected from this crack. The duration of an ultrasound pulse is 200 milliseconds. Okay, so first of all, let's find the speed at 23 degrees. Yes, 23 degrees, excuse me. I don't know why I got confused. So 23 degrees is this point over there. So if we go up, okay, the speed is this one over there. So 4,115. Because if you notice, each little square is 1 degree in the x direction and 10 meters per second in the y direction. I hope I make sense. So, I mean, that's 10, and here that's 1 degree. Okay, so 115 meters per second is the speed. Doesn't look good. Let me write it again. So 4,115 meters per second is the speed. Now, what else do we need? Pulse, v pulse. So the pulse has to travel, right, back and forth. So 0.08 meters. Okay. Now the speed is distance per time, right? So time is distance over speed, or 0.08 over 4,115. So that's meters and then meters per second. So this time is equal to 19.4 microseconds, which is much smaller than 200 microseconds. Okay, so the echo comes back while the pulse is still emitted. Okay, actually, I'm going to use a clean page. So while the pulse, okay, the pulse is still emitted. Okay, so this is not going to work. Okay, so this will not work. So crack will not be detected. Okay. Okay, part B. Pulses of ultrasound with a higher frequency can be used to find cracks of shorter length. Explain why a higher frequency is used. And I think by shorter length here they mean, this is a large crack, okay? Or the crack that they show here. So they probably mean something small like that, okay? So let's answer it. Remember that the speed of a wave is equal to lambda times the frequency. Okay, not frequency squared. Sorry. So the speed is wavelength times frequency. So lambda is equal to the speed over the frequency. So with v constant, right? If f increases, lambda decreases. Okay, so shorter lambda means less diffraction. Okay, when the let me try to make better letters. When the ultrasound travels through material. Okay, so this means that the ultrasound is less likely to bend and more likely to return and give a better reflection. Okay, I hope this makes sense, and let me show you. So what we mean by that is if it has a large wavelength, okay, it will go past the crack. Okay, simple as that. If the wavelength is short though, something like this, it will hit the crack and return. So it has a higher probability of hitting a small crack, pretty much. and be reflected and come back and be detected. Okay, so that's the answer. Okay, let's move on to question 14 now. Okay, 14, the photograph shows an electric bicycle. The battery contains several identical cells connected in series. Each cell has an EMF of 1.5 volts. One cell is removed from the battery and connected in the circuit shown. When the resistance of the variable resistor is 10 ohms, the reading on the voltmeter is 1.4 volts. Calculate the internal resistance of the cell. Okay, first of all, let's find the current in this circuit, which is going to be equal to the measured voltage, so V over the resistance, so this resistance and this voltage, okay? So 1.4 volts over 10 yields 0.14 amps, okay? Now, if this battery has an internal resistor, it means that the measured voltage is going to be equal to the EMF of the battery minus the voltage drop at the internal resistance. So minus I times the internal resistance. Or you can also say that the voltage that we measure plus the voltage drop in the internal resistance is equal to the voltage of the battery. Okay, so I times R is E minus V, so R is E minus V over I, so that's a minus, I'm sorry. So R is 0.1 over 0.14, which yields 0.71 ohms. Okay, so 0.71 ohms is the answer. Okay, moving on. B, the battery in an electric bicycle gets warm when the battery supplies power to the motor in the bicycle. Explain why the battery gets hot when the bicycle is going up a steep hill. So climbing a steep hill, what did I write? A steep hill, excuse me, takes more energy. Against gravity, right, than traveling at a flat road. Okay, now since power is equal to the current times voltage, okay, delivering more power at roughly the same V. Okay, and why is it the same V? Because it's the same battery, right? So the voltage provided is about the same. Okay, so to deliver more power at the same V, we need, so delivering more power at roughly the same V, we need more current drawn from the battery. Okay, now larger current means larger voltage drop across the internal resistance, right? The internal resistance, since the voltage across the internal resistance is I times R, right? Now, since power is I squared times R and power is dissipated as heat, comma, right? If I increases, P increases, so heat increases. Okay, I hope this makes sense. If it doesn't make sense, write me in the comments. I always reply, but try to understand the arguments. Okay, I mean, the battery provides a constant voltage, so to gain more power, we need more current taken out of that battery. Okay, so more current taken out, so higher current means a higher current passes through the internal resistance, which means that we have more heat created, pretty much. Okay, so that's a simpler way to describe what's going on. Let's move on to question 15 now. Okay, 15. The diagram shows apparatus used to demonstrate the diffraction of an electron beam in a school laboratory. Okay, so we have the electron beam passing through graphite, a vacuum, and a curved fluorescent screen. A beam of electrons is accelerated by a high potential difference towards a piece of graphite. The graphite diffracts the electron beam, producing a diffraction pattern on the fluorescent screen. State what is meant by diffraction. So, diffraction is the spreading of a wave, of a wave, which happens, oops, yes, which happens when waves pass through gaps or obstacles. So, I mean, uh, let me do it here. So, if we have a gap and there is a wave coming in, it diffracts like that. Okay, so that's the story. Okay, B. An electron is accelerated through a potential difference of 4.9 kilovolts. Show that the de Broglie wavelength for the electron is about 1.8 times 10 to the minus 11 meters. Okay, now Prince de Broglie's wavelength is h over p. Why Prince? Because he was a member of the royalty or an aristocratic family, something like that. Look him up. So lambda is h over p, but how can we find p? Remember that the kinetic energy is equal to p squared over 2m. So the electrons will have some kinetic energy in this region there, okay? And that kinetic energy is going to be provided by the accelerating potential. So this kinetic energy is going to be equal to the charge of the electron times the voltage, right? So P is pretty much 2 times the mass of the electron times the charge of the electron times the voltage, all inside the square root, okay? So we can find lambda as h over the square root of 2 times m times e times the voltage. I don't know why I extended the fraction for so long. Okay, so we are gonna go to a clean page over here. Okay, so this is equal to 6.63 times 10 to the negative 34, and this is joules times seconds. Remember that I think I didn't mention it in this video. For those of you who are watching my videos for the first time, I tried to arrive at the final algebraic expression for the quantity we are searching, and then I plug in numbers and I put all the numbers to the left and all the units to the right. Okay, I hope this makes sense. And then in the denominator, we will have the square root of 2 times 9.11 times 10 to the negative 31. What are the units of this? That's kilograms. And the kilograms will be under a square root. I know it doesn't make much sense, but bear with me. I'm going to show you something. Okay. So, okay, that's the square. Okay, let's try again. Okay, perfect. That's the square root of kilograms. Okay, don't be afraid of using units inside of powers. It's okay. Times 1.6 times 10 to the negative 19. What are the units for this? Coulombs, right? And then times the voltage, which is 4,900. And I'm gonna have to take this thing and move it down here because there's no more space. Okay, what are the units for the potential? Volts, right? But volts, okay, I'm gonna show you later. Okay, so let's write them like that. Okay, and if we carry the calculation, we'll find 1.75 times 10 to the negative 11. Okay, and this should be meters. Okay, so these units should evaluate to meters. Do they, though? Let's see. So we have joules times seconds, and then in the denominator, excuse me, we have kilograms times coulombs, and then recall that volts are joules per coulomb. Okay, so we have that nice cancellation. Okay, now joules can be expressed as kilograms times meter squared over second squared, and then we have the seconds in the numerator. Okay, why? Because remember that the kinetic energy is 1/2 mv squared, so joules are equal to kilograms times meter squared over second squared in base units, right? Okay, so, and then we still have this nasty square root, okay? But let's write it like this. So we have kilograms, and then we have, again, that's a joule, so kilograms times meter squared over second squared. Okay, let's keep going. I hope I didn't scare you. So that's kilograms, meter squared, and then seconds. And then we have second squared. And then in this root, we have kilograms squared, meter squared over second squared. And if we take the square root of this, we will have, if we take the square root, we will have kilograms meters per second, okay? And now look at this, it's beautiful. So kilograms cancel. Then we have second squared in the denominator canceling with these two, and then meters cancel, and we are left with meters, okay? Which is the answer we were hoping to find. Okay, this goes a little bit beyond scope. I mean, it's fine during a test to just code there that this answer is in meters, it's fine, but it's good to work these things out for practice so you understand deeper about what's going on. Okay, moving on. We're done with this. So part 2, a student suggests that the beam of electrons would produce a diffraction pattern if a diffraction grating with 5,000 lines per centimeter was used. Deduce whether a second order maximum will be clearly visible on a screen. The screen is placed about a meter away from the grating. Okay, so d sine theta is the order of the maximum times lambda. Okay, we need d, so d is 1 over 5,000, and that's lines per centimeter, right? Which we can write as 2 times 10 to the negative 6 meters, pretty much, okay? And let's combine these two. So sine theta is going to be 2 times the wavelength, which is 1.8 times 10 to the negative 11, over 2 times 10 to the negative 6. And this 2 over here is because it's a second order maximum, okay? So these yields, let me see, 1.8, actually it's easier. So we get 1.8 times 10 to the negative 5. And here we have meters over meters. So this cancel because sine theta should be a pure number, no dimensions, right? Okay, that's a really small angle, okay? So tiny, so very tiny angle, because in this case sine theta is approximately equal to theta. I'm going to write it up here. So sine theta is approximately equal to theta. So, and it's going to be approximately equal to 1.8 times 10 to the minus 5 radians. I'm using radians now because this is how the approximation works. So if you claim this, you need to use theta in radians, okay? So very tiny angle, because even in radians, I mean, if you want to convert it to degrees, you will have to multiply by 180 over pi. So that's it's a very small factor. 180 over pi is 57 times 1.8 times 10 to the negative 5. That's going to be about 10 to the negative 3 degrees, okay? That's a very small, sort of very tiny angle, so not visible. So we are talking about something like this. So it's like this is the central maximum, and then the next maximum is, I mean, this is the tiny angle that we are talking about, okay? So the first order maximum is going to be practically on top of I mean, that's exaggerated over there, okay? So you're not going to see second order maximum, okay? So not visible is the answer, okay? Moving on to question number 16. Okay, 16. A student connected the circuit shown. The battery has an EMF of 6 volts and negligible internal resistance. Okay, that's good. A, state what is meant by an EMF of 6 volts. So an EMF of 6 volts means that every coulomb pushed by the battery has a 6 joule energy. Okay, that's the answer. B, the reading on the voltmeter is 1.64 volts. Show that the reading on the ammeter is about 20 milliamps. Okay, so that's a 6 volts battery, that's 1.64. Okay, so to find the current, we're going to use this resistance. Okay, how? 6 volts is going to be shared by the two arrangements there. Okay, so this system of parallel resistors and the 200 ohms resistor. Okay, so 1.64 plus V, let's call it 200. Okay, that's a subscript. Okay, don't get confused. So the voltage of the 200 ohms resistor is going to be 4.36 volts. Okay, that's nice. 36. Don't know why I can't write the 6 today. Okay, now Ohm's law says that R is V over I, so I is V over R. So in our case, we're going to have 4.36 over 200, which yields 21.8 milliamps, which is about 22 milliamps, which is what you're going to measure in your ammeter. Okay, part 2. Determine the resistance of resistor X. Okay, the voltage across the parallel combination is 1.64 volts, so we're going to use that. So the voltage is going to be I, let's call it parallel. Okay, so these two lines mean parallel. Okay, I hope this makes sense. So V parallel is I times R parallel. Okay, so R parallel is going to be 1.64 over 21.8 times 10 to the negative 3. So that's 75.23 ohms. Okay, now 1 over R parallel is going to be 1 over Rx, the unknown one, plus 1 over, actually, let's plug in 1 over 75, 1 over 75.2, which is the combination, the R parallel. 1 over 75 is 1 over Rx plus 1 over 100. So 1 over Rx is 3.29 times 10 to the negative 3 ohms to the minus 1. So Rx is 303.7 ohms. Okay, so 304, so close to that. Okay, part 3. Determine the power dissipated in the 100 ohms resistor. So for some reason I forgot to solve this in my notes. I don't know why. So I don't know. I was rushing and maybe I skipped it by accident. Things like that happen. Okay, so let's see which one is the easiest to use. So the 100 ohms. Okay, so we can use that power is V squared over R. So we have the voltage across the 100 ohms resistor is the same as the resistor across X, which is 1.64 squared over 100, and I'm gonna need to use my calculator really quick. 1.64 squared over 100, so 2.7, so 2.7 times 10 to the negative 2 watts. Okay, and why is watts? I am adamant about these things, and here I didn't say anything. So we have volts squared over ohms. Okay, so these are the units. You don't need to do these things. I'm just being a little bit of a pedantic. So voltage is joule squared over coulomb squared, and then ohms is resistance is voltage over current. So the units for ohms is volts per ampere, right? So we have another joules per coulomb pretty much, which cancels, okay? And then times, let me see, and then over amperes, okay? Which yields joules per coulomb and then coulombs per second. And then we get joules per second, which is watts. Okay. All right. Part C. The student makes the following prediction. If I switch the positions of the 100 ohm resistor and the 200 ohm resistor, then the reading on the voltmeter will increase. Discuss the student's prediction. You do not need to include calculations in your answer. So if we switch the resistors, pretty much we're going to take this one. Let me erase. So we'll take this one and put it there and then exchange like that. Okay, so if we exchange the resistors, so if we switch the resistors, okay, R parallel increases. Okay, the total resistance R total of the circuit decreases, okay, because we have the smaller resistance here where the 200 ohms resistor used to be. Okay, so the current, okay, I need extra space. Okay, so the current will increase in the circuit. Okay, now with current increasing and the R parallel increasing, the voltage across the parallel combination will increase. So the student is right. Okay, I hope this makes sense. We are ready to move on to the next question, which is question 17. Okay, a vibrating tuning fork is placed near the open end of a tube that is closed at the other end as shown. Okay, A is a long writing problem. Describe how a stationary wave is formed inside the tube. I forgot to comment on this. So long form answers provide 6 marks, so they usually need about 6 sentences to justify them. But the same goes for other long writing problems. So if they provide 4 marks, you usually have to provide 4 arguments. So anyway, I hope this makes sense. So let's start. So the tuning fork, okay, vibrates and produces a sound wave in the air. Okay, this wave travels down the tube and reflects off the closed end. Okay, the reflected wave superposes with the incoming wave. Okay, where the two waves are in phase. Okay, they reinforce, they become larger. Okay, where they are in antiphase, they cancel. Okay, so actually I'm gonna need a clean page. So reinforcement means that we get antinodes, and where they cancel we will have nodes. Okay, the closed end is a node and the open end is an antinode. Okay, so that's the answer. Let's move on. B, when the length of the tube was 20.4 centimeters, the simplest possible stationary wave was formed inside the tube. Calculate the frequency of the sound wave, of the sound produced by the tube. So what's going on is that if this is a tube, do we actually let's go and use the scheme that they give us. So this is what's going on. Excuse me. So this is what's going on. Okay. Oops. Let me try again. So something like this. Okay, so this is a node and this is an antinode. Okay, so you see that the length of the cube is 1/4 of a wavelength. So lambda, the length of the tube is 1/4 of a wavelength for the basic frequency. Okay, let's go back. So we know that the velocity of the wave is going to be lambda times the frequency, but we need the frequency, which is v over lambda, which is v over 4L, which is 340 over 4 times 0.204. Okay, so we get a frequency of 416.7 hertz. Okay. Now, part 2, the actual frequency of the sound produced by the tube is slightly less than the calculated value. Suggest why. So the problem is that the antinode forms a bit outside, a bit outside the open end. Okay, so let's go back again. Okay, so what's really going on is, let's erase this, is that something like this probably. Okay, so the antinode is a little bit outside. It's a little bit outside the open end of the tube. Okay, so this means that lambda is larger than 4L. Okay, so f is smaller than 416.7 hertz. Okay, and we know this because they say that the frequency, the actual frequency, is slightly less. Okay, so the only way for that to happen is that the wavelength is longer. And why is it longer? Because it extends a little bit outside the tube. So that's the answer. Okay, and we are left with only one question in this test, which we will cover right now. So question 18, some types of glue can be hardened by exposure to UV light. Question A, one type of UV lamp contains mercury atoms in an evacuated glass tube. When a large potential difference is applied between two electrodes in the tube, electrons move between the two electrodes. These electrons collide with the mercury atoms in the tube. These mercury atoms then emit photons. Explain why the mercury atoms emit photons. Okay, so what's happening is that electrons collide. So free electrons collide with electrons that move around Mercury, okay, pushing them to higher levels. So let's use a clean page because I will need some space. So, I mean, this is the tube, okay, and let's say that, this is exaggerated, but okay, we have a mercury atom that has electrons orbiting around it, okay, and inside this tube, there are electrons moving, okay, so these electrons might go and hit this electron, for example, and make it jump to another level. Okay, and then as it de-excites to the ground state, it emits photons. Okay, I hope it makes sense. So the de-excitation of promoted electrons gives off light. Okay, let's go to part B. A technician is replacing the screen on a mobile phone. Okay, he spreads a layer of glue over the phone surface and attaches the glass screen. Excuse me. The glue is then hardened when exposed to UV light. The equipment used and screen dimensions are as shown in the following diagram. Okay, so that's the mobile phone over here, and we see the front view. This is a side view, okay? And they shine light that hardens the glue, as they claim. I've never seen this before, to be honest. Let me know if you did, okay? This is the first time I'm hearing about this, to be honest. Okay, the intensity of the UV light received on the screen is 50 milliwatts per square centimeter. The glue takes 25 seconds to harden, okay? The question is, show that the total energy incident on the glass screen during this time is about 130 joules. This is a good opportunity for us to use dimensional analysis. So they give us the fact that 50, where is it? The intensity of the UV light is 50 milliwatts per square centimeters. So 50 times 10 to the negative 3 milliwatts are joules per second, and then we have 1 over square meter in the denominator, okay? And then the dimensions of the screen are 7.15 times 14.7 centimeters squared. I'm not converting the centimeters because we need them, okay? So that's the dimensions. And then this takes 25 seconds, so you have to multiply by 25 seconds. So usually I don't solve problems like this, but I'm making an exception here, so 25 seconds. Okay, so seconds cancel, then centimeter square cancel, and we are left with joules, okay? And actually this is a unit, this is energy, okay? So the energy is 131.4 joules. Okay, so that's the energy. Part 2. Determine the number of photons incident on the glass screen in this time, and they give you the wavelength of UV light as 395 nanometers. Okay, so the energy of the photon is h times the frequency, or h times c over lambda. Okay, so 6.63 times 10 to the negative 34 times 3 times 10 to the 8, and the units are joules times second, and then meters per second. Okay, and then lambda is 395 times 10 to the negative 9, and that's meters. Okay, so the energy of one photon is 5.04 times 10 to the negative 19, excuse me, 19 joules. Okay, and if we divide, so energy total over energy of the photon will give you the number of photons. So that's 131.4 joules over 5.04 times 10 to the negative 19 joules. So the number of photons is 2.61 times 10 to the 20 photons. Okay, beautiful. Let's move on. Okay, part C. The potential difference applied between the electrodes in the UV lamp is increased. Explain the effect this will have on the frequency of the UV light produced by the lamp. So the thing is that the energy levels are fixed, okay? But since electrons will now have a higher energy, they might promote the mercury's electrons into higher levels. Okay, I will need a clean page. So the frequency, which is equal to the energy over h, might increase actually. Might increase. But this is not because something will change with the atoms. I mean, the atoms are the same, their energy levels are the same. It's just that the electrons have more energy available, so they might promote electrons from Mercury to higher energy levels than before. Okay, so you might observe some UV light of higher frequency. Okay, so that's the answer. Okay, part D. Suggest why the hardening time of the glue is reduced if the UV lamp is moved closer to the mobile phone screen. Okay, so the intensity is power over 4 pi r squared. So since r decreases, the intensity of the light increases, okay? Uh, so intensity increases since the distance, okay, the distance decreases. Now more photons per second are now available, okay, hence more energy, okay, so hence the glue hardens faster. Okay, and that's a complete answer. Okay, so this was unit 2 from what was it May? Let me remember. Was it May or January? No, I'm confused. From May, excuse me, from May 2025. Okay, I hope these videos are useful. The channel is growing, but not as fast as I'd like it to grow. And again, as I said, I don't want this to end up being a channel just for past papers. But okay, I will keep uploading past papers because I like it and people find help through these videos. So I will keep uploading those, but gradually I'm gonna add more content. And I already started with going through a research paper, okay, and I showed some results from that research paper on the screen, and people were excited about that. So I will keep doing that and keep uploading past papers. Let me know what you think about these videos. Like and subscribe. Please promote my channel to other people who might find it useful. And see you in the next video, guys. Bye.